A fundamental question we might have is, what is a vector? Graphically, we express a vector with just an arrow, whereas we might express a location as a point. So we kind of understand points already. They're locations in space, and their location is usually denoted by some coordinate, which might be something like 1, 2. So if I give you a point 1, 2, then I'm saying on the xy plane, which we might call R2, that at the location 1 over and 2 up, I've got the point 1, 2. But a vector is a movement. It doesn't have a location, it's discussing how something changes. So in a sense, there's a big difference here. Points are static, whereas vectors might be something that's dynamic. When we represent a vector on the xy plane, let's say we also represent it with the same coordinates, but again, we're going to distinguish them by putting angle brackets like this. So if I do angle bracket 1, 2, then I'm talking about a movement in R2 that says I do one movement over in the x direction and 2 movements up in the y direction. So if I start at the origin, then where I'm moving to is in fact the location that we discussed here. But vectors don't have locations, points do. So even though I could think of this vector as starting here in the origin, I could also think of it as existing here. And it doesn't really matter where I draw it. So I can put it anywhere on here, and it's still the same vector. Whereas if I try to move a location, as soon as I consider a different location, I have to have a different coordinate for it. So this one, even though it looks the same, it's just a dot, my coordinate is 3, 1. Whereas if I bring this down here, it's still the same vector. This is still 1, 2. There's no difference. So vectors versus points. There's the notation. We're going to write them with angle brackets. So we might write x, y as a value, or x, y, z. Doesn't really matter how many dimensions we have. Whereas a point, we're going to use just your standard parenthesis. These are 2 parentheses as opposed to angle brackets. X, y, z. And again, it doesn't matter the dimension. I just add it on. So there's the notation aspect. Then there's the conceptual difference, which is a vector is somewhat like a movement in space, whereas a point is really more of a location. Then there's the depiction on the graph. A vector we represent with an arrow versus a point. And then lastly, where you draw it. So where you draw it, so it doesn't matter for a vector. You can technically draw it anywhere, but it does matter when it's a point. So let's talk about what are the features of vectors. So vectors really have 2 components to them, in a sense. One is the direction that they're pointed, and the other one is the length, which we call the magnitude. When I draw something like a 2-dimensional plane, so we have R2 here, I have a whole host of directions that I can point to. There are infinitely many such directions. Here I've drawn 9, so I've drawn 9 directions. And then there's this notion of a length. So if I consider one direction, let's say this one, I could draw it going this length, or I could draw it going this length. And it technically means something different, even though they look like they're right on top of each other. Now remember, even though I'm drawing it coming from the origin, that's an arbitrary choice. So we draw from the origin just for convenience, right? It's sort of a natural center for our graph, but really, I could have drawn this direction, coming out of some arbitrary point here, and that's totally okay too. It really means the same thing. So let's think about this idea of direction. And for ease, let's stick to the 2 dimensions. So we have x, y, so we're working in R2. Now, let's say I have 2 vectors that are the same length, meaning they have the same magnitude. We embed all of these things at the origin, and I said earlier that we draw it for convenience. The convenience is that we get to see something like angles here. So here I have an angle, and here I have an angle. So let's say the blue vector forms an angle with the x-axis of phi, and that the green angle forms an angle of theta. I actually can figure out what this vector is, what the motion is that it's making. So a vector, it's going to have an ending point and a starting point. And all I need to figure out is how much did I go in the x direction, and then how much did I go in the y direction. Because I started from 0, this is just the coordinate for this point. So my vector should be L cosine phi, L sine phi. Similarly, the green vector, I'm going to consider how far did I move in the x direction and how far did I move in the y direction. And I can capture that with all the information I have. And that's again going to be L cosine theta. There shouldn't be a mark there, sorry. L sine theta. And so my direction is really well captured by the angle that I have. But of course, we might not think about it in this polar form. Once I have L in theta or L in phi, I can figure out what the coordinates are, what the x direction is and what the y direction is. And notice that in this polar system, my length is already given, right? So I know what my magnitudes are. So let's do a quick exercise. Suppose that I'm given the following vector. I'm given 5 cosine 30, 5 sine 30. So what's the magnitude? The answer, of course, is 5, because it's already in that form. Now suppose I'm asked a slightly different question. I have vector 1, 2, like the one we started with. What's the magnitude? Well, oh, and then the second question I might ask is what's the angle? So let's graph this, just so we have a nice visual. Here we're going to move over 1 and we're going to go up 2, and this is our vector. Now how can I figure out the length? So I want you to take a moment and think about this. Look at this picture and tell me, how would you figure out the length of this arrow, this vector? So if you noticed that we have this nice right triangle being formed, and that you could use the Pythagorean theorem, or if you notice that we're really thinking about the distance from 0 to this arrow here, and then deduce that you could use the Pythagorean theorem, you've got exactly the right idea. Right, we've got a distance of 1 here and a distance of 2 here. So the distance of the arrow is the distance of the corresponding hypotenuse. Right, so our magnitude is going to be the square root of 1 squared plus 2 squared, which is the square root of 5. So that's the length. Now let's take a moment to talk a little bit about notation. In the notes, I might label a vector v and I would write it as bold. But when you're writing, you can't really do that. So we often adopt a physics notation where we put a little arrow at the top, and that arrow indicates that I'm talking about a vector. So rather than write something like magnitude, I instead might write something like the absolute value of the vector, because the absolute value is in a sense just distance. And so the magnitude is the absolute value of the vector, which is really the length of it, and so that's how we'll represent it. The next question, so we've got this one done. The next question is to ask, what is the corresponding angle? So how would you figure out the angle here? Again, we can use trigonometry, right? We've got now this distance as root 5. So we have a nice right triangle here that captures all of our information. And we're interested in this angle, theta. So if I take 2 over the square root of 5, what trigonometric function might that be? Well, that's opposite over hypotenuse, so that must be sine. So if I take sine inverse of this fraction, I should get theta. Alternatively, I could have done cosine inverse of 1 over root 5, or if I never solved for root 5, I could do opposite over adjacent, which would be tangent inverse of 2 over 1. And each one of these should give me the same answer. But be mindful about the sign, because these inverse functions, well, hopefully you remember from trig that there's some complication here. If you're not sure what I'm talking about, take a moment and review So let's take a moment and quickly summarize. The magnitude of a two-dimensional vector is represented by the symbol of absolute values, and we write the square root of each entry of the vector. So x squared plus y squared if v is equal to x comma y. And the angle that it makes, we can think of theta as being tangent inverse of y over x. But now the question is, what happens with our vector if we're thinking about it in 3 dimensions? So it's clear to see how to represent it in polar coordinates and how to represent it in Cartesian coordinates, right? This would be Cartesian coordinates, whereas polar coordinates, the same vector, would be, let's call this L. So let's draw our 3-dimensional axes. And remember that this guy is coming out of the page. So you should imagine it coming out of your monitor. So now if I have some vector going out, and let's draw a shadow for this vector so we can kind of see that it's coming out into the plane. And we'll give it the coordinates 2, 3, let's say 1. And we'll call this vector W. The question is, I've got it now represented in Cartesian coordinates in 3 dimensions, so we're in R3. Well, we definitely can figure out the angle that's made in the xy plane, right? And we can do that using the same stuff that we did earlier. Our angle on the xy plane is going to be the same. So theta should be tangent inverse of y over x. Now the question is, how do I figure out the angle with the xy plane and z, right? There's an additional angle here that we're going to call phi, right? Because we need 2 angles here. So phi should equal something. And I want you to, I'm going to leave this as an exercise to think about, how should you find phi? Now the question you should also be asking yourself is, what is the magnitude? Just like distance in 3 dimensions, the magnitude in 3 dimensions is actually the same. We're going to take the square root of the sum of the first entry squared, second entry squared, and the third entry squared. This is going to give us the square root of 4 plus 9 plus 1, which is the square root of 14. And that's our length. So let's do some examples. We're going to find a 2-dimensional vector of length 3 at 135 degrees. Okay, so let's first graph it, just so again we have some kind of notion of what's going on. So here's my graph of R2. 135 degrees. Well, from here to here is 90, and from here to here is 90 to 180. So we're going from 0 to 90, 90 to 180. So we should expect 135 to be in this quadrant, in the second quadrant. How far is it? Well, 135 is 45 degrees from 90. So from here to here, I should have 45 degrees. Now I know enough to graph it. So I'm looking at a vector like this, where this is 45 degrees, because of course the other side is. And the length is equal to 3. I should get 3 cosine of 135 degrees, 3 sine of 135 degrees. Now, let's recall how we figure out what sine and cosine are using just the stuff we learn about the unit circle. So if this is 45 degrees, then I'm thinking about a special triangle that we think of as 1, 1, and square root of 2. So our angle, our cosine, is adjacent over hypotenuse, so this should be negative 1 over square root of 2, because this side is negative 1, because this side is negative, and this side is positive. And then here we should get 1 over square root of 2. So my actual answer, if I simplify, is just going to be negative 3 over root 2, comma 3 over root 2. Okay, let's do another example. Construct a vector from A, which is 1, 3, and 5, to B, which is 1, 0, and 7. Okay, so remember that a vector is movement. So we want to ask ourselves, what was the change for each dimension, right? How much did I change in the x direction? I didn't change at all, right? Because I went from 1 to 1, so I didn't go anywhere. So my vector should have a first entry of 0. Now my second entry, I started at 3 and I ended up at 0. So it looks like I moved backwards 3 steps. So my second entry should be -3. My third entry, I started at 5 and I moved to 7. So it looked like I moved forward 2 steps, and so I should have a +2. Now, what I was really doing was I was doing where I started, so 1 minus where I ended, -1, or 0 minus 3, or 7 minus 5. Sorry, I think I said that backwards. Basically, I want the difference to be where I ended minus where I started. Okay, let's do another example. So we want to construct a vector. What is the magnitude of -2, 1, and -5? So I might have a hard time graphing this, but let's do it anyway. So here I have a representation of the positive coordinates, x, y, z. If I want the negative coordinates, I'll sort of think about them as going into the page or down. Now, let's graph our points or our location. So if I go -2 steps, then I can go a +1 step. So I'm looking at here. And then I need to move up or move down 5 steps. So it's like 1, 2, 3, 4, 5. So I might think of my vector as going down and over like this. Now, if I want to keep in mind where I'm located, I can sort of draw a weird shadow from on the XY plane to kind of help me see, right, it's going backward into the screen. Now, what would my magnitude be? I think it's very helpful to look at the graph and try to estimate roughly what would be a reasonable answer. I don't think this answer should be, it should be more than 1 but less than 10. So let's actually figure it out. So my magnitude, let's label this V, of V is the square root of -2 squared plus 1 squared plus -5 squared. The square root of 4 plus 1 plus 25, which is the square root of 30. And the square root of 30 is our answer, but let's make sure we can understand it. Square root of 30, it's going to be less than 6, right, because this guy is equal to the square root of 36, but it's going to be bigger than 5, because this guy is the square root of 25. So if I wanted to estimate where this would be, I would guess that it's sort of smack dab in the middle. Maybe it's about 5.5. So vectors aren't just items, like they're not just arrows floating in space. They're things we can, add and subtract, which is pretty cool. So if I have one vector going this way, and I have another vector going this way, and I have a third vector going maybe this way, I'm able to add them together. And effectively, when I add them together, I'm bringing them next to each other. And so when I think about where they bring me, the net result is, in fact, their sum. So if I started here and I ended here, that's equivalent, this vector, this gray vector, is equivalent to the addition of the green, blue, and red. So the question is, how do I add them? Well, if I think of each one as being a movement, I can add the movements, right? So, for example, let's add an R2 graph, so that way it's easy for us to see. And let me have one vector, that's my favorite, 1, 2. I use this too much, we'll call it V. And let's have a second vector, green, be in this direction, and we'll say that this is -3, 1. So if I wanted to capture this vector and this vector, and I wanted to add them together, the resulting vector should look something like this. Right? Notice that I had to write this on the side. because I really need to think about these movements happening in succession. And in this picture, they're not happening in succession, they're all happening from the origin. Whereas here, I've written it so that there's the green one first and then the blue one second. So let's add them. So if I moved 1 step in the positive direction and then I moved 3 steps in the negative direction, I've moved a total of 2 steps in the negative direction, right? By adding these two numbers, I see that. So my resultant vector, oh, I forgot to name the other vector, let's call it W. So my resultant vector is v plus w. Its first entry should be -2. Now the second, it should be 2 in the positive y direction and 1 in the positive y direction. So I moved a total of 3. And that's what this vector should be, -2, 3. So if I graph it, I get something all the way up here. Now notice that in this picture, it's really hard to tell that this is my resultant vector. It's not easy to see the sum, right? Looking at this picture, it's not immediately obvious that, oh, I should be careful about using arrows. It's not immediately obvious that the gray arrow is the sum of the green and blue arrows. But when I draw it here, this is much easier to understand. So while we use this convention of drawing things from the origin, we only use it whenever it's helpful to us. When we're thinking about addition, we might think about it more in a picture like this. This is generally a better picture for conceptual reasons. Okay? So we can add them together. What do you think happens when you subtract them? It's exactly the same. So let's actually pull our same example. And remember that this vector here is our sum. It's v plus w. Okay, so let's say we wanted to figure out v minus w. Well, if you guessed that you should just subtract them component-wise, you're absolutely correct. It's going to be v, the entry here, minus w. So 1 minus -3 and 2 minus 1. And that's going to give us 4, 1. And so now our resultant is 4 over and 1 up. So this is in fact v minus w. Now I have a question for you. What about w minus v? Is that going to be the same as v minus w? What do you think the answer should be? If you said no, then you're absolutely correct. So remember that when you subtract two numbers, the order of course matters. So if we wanted something like w minus v, we'd need to start at v or w and subtract out v. So our first entry would be -4, and our second entry would be 1 minus 2, so -1. So in fact, we would have this vector. Now, what do you notice about the relationship between these two? Right? This one and this one, they look really similar, but the big difference is that they're flipped, right? One is the flip of the other. Depending on what perspective you want to take, you can think of one as being the other flipped, or vice versa, right? They're the negative. And this is in fact what happens when you multiply any vector by -1. So this is in fact equal to -1 times v minus w. Now I want you to notice something. -1 is what we call a scalar. It's a constant. It's not a vector. And v minus w is a vector. So this brings us to the other aspect of arithmetic, which is that we can multiply. So let's summarize what we know so far. 1, we can add vectors. We can subtract vectors. We can multiply a vector by a scalar, which we haven't really covered yet. So let's go over that. So let's say I have some constant, c, times a vector v, and let's make our vector three-dimensional. So let's say that c is some number like 7, and my vector is 1, 1, 2. Well, how do you think you should multiply these? If you guess that you should distribute it across these various entries, you're absolutely correct. My vector ends up being 7, 7, 14. And that's it. That's the extent of multiplying by a scalar. But the big idea to know is that When I multiply by a scalar, I'm effectively making the arrow bigger. So if I, for example, have an arrow of this length, right? So let's say this is my vector v. Then when I multiply v by, say, 2, just like you'd expect, I'd end up with something parallel but twice as big. So 2v would in fact look like that. And then if I wanted to multiply it by something like negative 2v, it would be the same length, but it would point in the exact opposite direction. Now remember that the location doesn't matter. So even though I'm drawing them parallel, I could think of them back to back. Now lastly, let's say that we have some vector that's fairly large, something like this vector here. And let's say that this has a length, so this is my vector v, and let's say v has a length of 12. And now let's say that I want to find some vector that is exactly parallel to v, but of length 1. The big thing is that v is parallel to w, so they go in the same direction. Their corresponding angle would be the same. How could I find w? So take a moment and ask yourself, how would I figure this out? If you thought, well, why don't we just take v and divide by 12, you're exactly right. Whenever you divide a vector by its magnitude, you get the unit vector, a vector of length 1 that's parallel to your original vector. So now let's do some examples. If v is 1, 1, 2, what is 3.2v? Well, we'd really just multiply every entry by 3.2, so that would give us 3.2, 3.2, 6.4. Find the corresponding. So the unit vector, remember, has to have length 1, which means we're going to divide by the magnitude. My apologies, I just realized I left off the arrow. So in order to divide by the magnitude, we first need to find it. So the magnitude of v is going to be the square root of 1 squared plus 2 squared plus 1 squared, which is the square root of 1 plus 4 plus 1, square root of 6. So the unit vector is going to be the vector v divided by the magnitude of the vector, which again is a scalar, so we're okay doing that. We're not dividing two vectors, which would be bad. And that's going to give us 1 over the square root of 6, 2 over the square root of 6, and 1 over the square root of 6. Okay, so let's do a quick quiz. So what are some things we can and can't do? I say quick quiz. Let's do a quick review. So things we can do. We can add vectors, we can subtract vectors, and we can multiply by a scalar. We can divide by a scalar. What are some things we can't do? We can't technically multiply two vectors to get a third vector. There's a caveat here, and this caveat we'll see later lectures. And we'll talk about that a little bit later. We also can't divide two vectors. That's not possible. And that concludes our lecture on vectors.